The broadcast is now starting. All attendees are in listen-only mode.
Hi all, I can see people are joining slowly. We'll get started shortly. Hi everyone, I can see I think most people have joined, but we'll wait until around 2 minutes after the hour before we get started. Looks like most people have joined now. I don't see any more people starting to join. So yeah, maybe with that we can get going here. So just welcome to everybody. Welcome to another one of our FNBC's webinars, which are forming part of our full webinar series. So thank you for taking the time to attend. My name's Brett Patrick, and I'll be moderating the session here. So just before we get started, just a reminder that there is a questions area that you should be able to find on the software there. You may type in your queries throughout the session. You can raise your hand as well, but we'll wait until the end before taking any questions. So if I do miss seeing your hand during the talk, just try and raise it again, and I'll try and catch you at the end of the presentation. Today our webinar is on analyzing condensation in unique glazing systems. It will be presented by Neil Norris. Neil is a facade thermal performance specialist at Morrison Hershfield. He has a focus on the research and evaluation of the thermal performance of the building envelope, including 2D, 3D thermal modeling, and in-situ monitoring of real-life building systems. As a main contributor to the Building Envelope Thermal Bridging Guide, Neil has a deep understanding of how glazing systems performance and thermal bridging can impact the condensation resistance of assemblies. Neil has worked on numerous projects and with manufacturers to analyze and understand how their systems can be improved to prevent condensation buildup. And yeah, with that said, I'll pass it over to Neil and he'll get going here.
Thanks, Brett. Just to kind of check, everybody can see my screen and kind of do a quick chat check. You want to type in yes?
Should be good from our side. Yeah, good to go.
Okay. So yeah, today I'm just going to kind of be going over a little bit of condensation risk and how we analyze complex glazing systems to assess that risk. Kind of going through some case examples and just really highlighting how an effective way of undertaking these sorts of analysis when it's not an off-the-shelf sort of system. So to kind of just start us off is just the very basics of what it means to have condensation occur on the interior of our buildings. So condensation, very simply, is when water vapor in the air turns into actual liquid water, and when that appears on different interior surfaces. So that can occur under specific conditions, and what you need to have for that to happen is you need to have a fairly high degree of moisture in the air, coupled with a cold surface that's colder than the air temperature that something can condense on. Getting a little bit more technical, it's really related to kind of the amount of water that air can hold. So kind of reaching back into our psychrometrics, it's when it's related to the dew point of that air. So the dew point is the temperature at which air becomes saturated and really can't hold any more water. So if that has a certain amount of water vapor within that air at a certain temperature, if it cools down past that saturation point, then it has excess water, and condensation will form on any surface that is now below that dew point temperature. So the higher the amount of moisture that's in the air, which is related to the relative humidity of that air, then the higher the dew point is going to be. And coupled that with cold temperatures, so more anything that causes that interior surfaces to be colder than the interior air, well then that just makes it that much easier for condensate to form on a surface. Kind of going through a really quick example here. If we have a dry bulb temperature, so the air temperature is about 20 degrees, and we have about 40% RH. What do you just kind of type it in if you get a chance there. But what do you think the dew point is for something like that? So we can just follow along in our psychrometric chart. We have our kind of relative humidity, or our interior temperature down here at 20 degrees. We just follow that up to the line where that represents 40% relative humidity, and then just carry that across to find out what our dew point temperature will be. So that's somewhere around 6 degrees. So really, when you have 40% RH in the air, and the air is at about 20 degrees, if that air touches anything that is at 6 degrees and lower, then you have the potential for condensation to form on that surface. So what are the typical negative consequences? A lot of our buildings, when we talk about this, it's typically either commercial or residential style type buildings. So the negative consequences really fall out to these main three sort of items here. So the first one is durability. So if you have a lot of moisture being formed on glazing systems, then if that moisture comes off the glazing system, or can even damage the glazing system itself, but mainly if it comes off the glazing system and hits our interior finishes, if they're not durable finishes that are susceptible to moisture damage, then they'll degrade. If they're left too long, and so in one sense, after the degradation, then that can impact the aesthetics. You can get staining and warping of those interior finishes, or even breaking down some of the structural elements there, if it's say wood or other materials like that are susceptible. And then if it's left too long, then what you end up having happen is you potential for mold to grow, causing kind of health issues. So these are kind of the main items to watch out for when we're talking about condensation, and that's really been the focus of most of our buildings when we talk about condensation risks, whether it's low-rise residential, high-rise, or even office buildings. And that's kind of reflected as well in our local codes, whether it's here in BC or in the national building codes. But essentially, just highlights the fact that what we're trying to achieve with keeping condensation low is it should be sufficiently rare enough, or the quantities accumulated should be sufficiently small and dry rapidly enough to avoid those material deteriorations and the growth of those mold particles. So that's kind of been the focus now. Whether or not we actually have a specific target, it's mainly left up to the designers. And that's somewhat reflected as well here in terms of what we need to achieve. It essentially lays out, it says it's recommended that designers specify those condensation values to minimize the potential for condensation, because there's no real set rule. Every kind of condition is a little bit different, so you have to be able to use as a designer, designers have to be able to use some judgment to figure out, well, what are the targets we need to have to make sure we're not causing excess moisture to be accumulated on around windows. So knowing that it's a coupling of both the surface temperatures and the interior humidity, then we need to those two. There's a little bit of a balance. It's if one gets too high, the other one, it gets a lot more easier to condense on surfaces. So we just got to figure out where those sources are coming from. So the first one for interior moisture, a lot of our moisture comes from people, right? It's you yourself in the building, you're breathing, you're giving off moisture throughout the day. In certain cases, if you're residential buildings, it can be plants. Another really big one is from air leakage. So if you have leaky windows, or you have a lot of operables that aren't very airtight, then you will get some of that moisture coming in from the outside and coming in through those leakage areas. This could, if you're in a residential building or a commercial building that has kitchens, then cooking will produce a lot of moisture. Here again, residential, it could be showers, or even commercial buildings or other types of these non-residential buildings. You could have water features, right? That also provide a lot of moisture into the space. On the other side, what creates cold surface temperatures? Again, air leakage can do that, right? If you have a lot of cracks or a lot of openings in your building and a lot of cold air, especially in the wintertime, is coming in, that can cool down those surfaces to make those surfaces even more susceptible to condensation. You could be dealing with windows that don't have great thermal breaks in them, so that you have very cold frame temperatures, right? Or it may be adjacent materials or adjacent walls where there's not a whole lot of insulation, and say if it's steel framed or it has a lot of thermal bridging, that's able to bring to kind of cool down a lot of those adjacent surfaces. Or it may be for windows, it may be the IGU, simply the IGU itself. It may not have a great U value in comparison to what the exterior temperature. So that can also create those cold condensive surfaces. Now that's when we kind of think about for the main reasons for preventing condensation in our typical commercial and residential building, but there are a great deal of unique projects out there that really call for a greater assessment and greater performance than just those code minimums. It's not just about preventing condensation simply to prevent mold growth or degradation of materials. While that's still important, there could be tons of other reasons why we want to have even better control of condensation on these types of unique projects. So certain ones to kind of consider. The first one that comes to mind for me is sporting stadiums, right? They have typically high occupancies, and they can have very strict requirements for minimizing condensation, right? There's a lot of opportunity, if they're enclosed spaces, enclosed stadiums. There's a lot of people generating a lot of moisture in that space, and there's a certain amount of mechanical equipment that's intended to take away that moisture, but at the same time, what are the risks of moisture appearing? So in a situation like this, you have a big open or enclosed roof that's, whether it's glazed or has some sort of polyethylene film sort of pillowed system, then if condensation starts to form on that, if it's really cold surfaces and there's a lot of people inside, then you end up potentially getting water drips on the inside of a building when it's all enclosed. And that could play a very important role for certain of these stadiums, because that may impact contracts or for different events that are held there, right? They're not typically owned specifically by the sporting leagues themselves. So it may be you have lots of other events that can occur in there, and they don't want to have to deal with dripping water on everyone. So that may be a stipulation in their contracts to hold those events. Another unique project could be a museum. So they typically have strict requirements on interior humidity to protect exhibits, and they may actually have in there that they maintain certain elevated levels of humidity. You don't want things too dry, especially when you're dealing with old materials, fibers, that kind of thing, just where it could break down. At the same time, you may not want to have it too elevated, but essentially what they're trying to do is maintain a certain level, especially in the wintertime, and maybe especially in locations where the winter air is quite dry. They may have that coupling of high humidity, higher than expected humidity, with cold exterior temperatures. So that can make it a little bit more susceptible to condensation. And a lot of these museum spaces are often used for events themselves, right? You may have functions, fundraisers, whatever. And maybe the architectural design of these spaces are intended for you to be able to see to the exterior, and it becomes a little bit, I guess, an aesthetic issue if you have a lot of condensation forming on these surfaces. And again, that can impact the ability for these types of event spaces to get these contracts down the road. Similarly, music halls, large event spaces, maybe recital spaces. Again, more event spaces, and that really want those clear views to the exterior. And then a lot of these types of buildings, whether it's museums or music halls or whatnot, cater to certain clientele that may push it to have more higher end finishes. So they want to keep those finishes quite well protected from condensation and degradation. So for all of these types of styles of buildings that employ complex glazing systems, when they're looking for strict requirements to control condensation that are above those code minimums, they often employ very, much more complicated facades. So they may have more connections or more features that are somewhat unique to that building. So, and then with that idea, you're using maybe custom systems or something else to accommodate that architectural intent. Maybe it may be a new type of system, or it may be something that's heavily modified to make work for a specific project. But really, it's to the point where any previous modeling or testing for those systems may not actually be applicable anymore. So when we need to think about how we approach analyzing these systems, we have to understand, it's probably not off the shelf. And because we're dealing with, very particular types of conditions, we want to have as close to the project type of specific analysis as we can to get that due diligence to make sure that this system actually works for what we're intending it to work for. And really, that goes without saying is that's not just in condensation, but also the other pieces to any kind of custom facade system, whether it be structural, fire, or other considerations. So these big projects are usually marquee. They have some funding to back them, and there's a lot of riding on the performance of these systems, right? You spend all this money to create this very beautiful facade. You need to make sure that it actually works and functions the way it's intended to. Now, how have we typically looked at condensation resistance from a couple different perspectives? Maybe from the manufacturing side, some of you have used the NFRC methodology from NFRC 500. That's the condensation resistance value. So really what that does is it tests kind of center of glass, edge of glass, different frame under different temperatures and interior conditions. And it kind of weights that into a single number, and it gives it a number between 1 and 100. So it's kind of give you the idea of how good this system is intended to perform for condensation resistance. Now, like with a lot of NFRC approaches, that could be very useful to compare product to product. Like, if this one has a rating of 60 and this one has a rating of 65, well, that one may be a little bit overall more effective for condensation resistance. However, that doesn't really help when you're trying to figure out, well, even if it has a better rating than another system, does it actually work on my project? And so, so this type of analysis doesn't really, you'd have to dig a little bit deeper, especially into how the systems were modeled and get that information to really figure out how you can take that number and apply it to your project, which can be a little bit difficult. So what we really need for project-specific modeling is you need things like the specific sizes of the components or glazing units or what we're looking at. And typically we want to look at, when we're looking at condensation resistance, we want to look at the worst case scenario, right? It may be the smallest of all the glazing systems that are there. It may not be the typical piece, but at least we know that that's probably going to be the worst case that we have. And really we want to find, are there critical locations that we think will have high thermal bridging, right? Maybe you'll have, some specific structural connections or some sort of penetration through your glazing system that will likely cool down the frames and be a higher risk for condensation. Then the second thing we want to look at is not just the project-specific system, but also the design conditions, right? We can go with the 99% design temperature, right? That only occurs less than 1% of the year if we wanted to have a conservative approach. We can take the average winter low temperatures, right? We can see for our particular location what maybe not the design temperature is, but what is going to be likely to occur for most of the winter. We can take a look at a whole range of temperatures. It could be the design temperature, average temperature, and other temperatures on shoulder seasons. But it really it comes down to how conservative you need to be and how thorough you need to be in your analysis, right? Every project is different. If there's a lot riding on the fact of minimizing or completely cutting out condensation, then maybe doing a lot more analysis or a bigger section of temperatures may be prudent for your particular project. So, without doing the condensation resistance factor, for project-specific modeling for condensation resistance, the first thing we need to get, obviously, is the actual surface temperatures, right? So depending on what the project conditions that you've selected, it could be multiple different exterior temperatures. And so what we need to go get for each one of those scenarios is the actual surface temperature under those model conditions. And what we also need to do is really highlight or find or pinpoint those critical condensating, first condensing surfaces. So where are our coldest temperatures that are occurring on our window? And that'll give us an idea of, like, where we need to focus in on, or where we need to pay attention to the most in order to kind of give a better assessment of the overall performance of the system. So if I kind of highlight here, in this case, for this particular system, we've got a window that's kind of nestled into a steel stud wall, kind of a punch window opening, and we would probably guess that our critical temperatures are probably going to be at the corner, along the edge of glass, maybe in around the steel studs, where we know maybe there's a clip system on the outside down here. And you can kind of highlight here, pointing out, yeah, this T2 may be quite cold. Here's T1 and here's T3, just at the corner. It's kind of highlight, obviously it stands out a little bit as to where those cold temperatures are on this assembly. The second thing to kind of consider is the temperature index. Now, this is something that there are kind of guidelines for in AMA and a couple other different sources. This is something that Passive House uses quite often. It's really creating a non-dimensional temperature so that you can take a temperature index and try to apply it over any type of temperature difference that you have. Doesn't matter what the climate conditions are. So really what it is it's a ratio between the inside and outside temperature. So it will always be between 0 and 1. So in a sense, you have exterior temperature is 0, interior temperature is 1. So if we had, say, 20 degrees inside and 0 degrees outside, well, a temperature index of about 0.5, that's halfway in the middle, will be about 10 degrees. So that tells us what that surface temperature would be. Now, if you take that same system and then say, well, now my exterior temperature is -10 degrees. So now you have between -10 and sorry, let's say -20 and 20 inside. So then our 0.5, our temperature index is still 0.5. It doesn't change, but now that surface temperature is now at 0 instead of at 10. So that's kind of how that system works. And then the last thing we kind of want to take a look at is, and this is something that I like using, is the allowable interior humidity. Now, often if you're a manufacturer, supplier, or even a consultant, building envelope consultant or whomever, or architect, you may not be the one that's actually looking at what the realistic humidities are on the interior. Potentially that goes back to the mechanical design. Now, what we can do though is really try to find out from these temperature, these condensation analyses, is, knowing how much humidity impacts the formation of condensation, we can find out what the maximum allowable humidity is on the interior before we get condensation. So that's kind of based on those critical surface temperatures that we've identified. And then we make sure whatever that critical surface temperature is, we then imagine it, if that were the dew point temperature, then what would the humidity need to be before it starts to condense on there. So it provides that highest level of interior moisture that can be present before that surface essentially becomes dropped below the dew point. Kind of show you a kind of like almost like a reverse example, right? If we have a surface that is at 6 degrees and we know our interior temperature is at 20 degrees, well, it's just kind of back calculating where do those two meet. And that kind of shows us that, yeah, it's about 40 degrees, 40% relative humidity. So if we have those two conditions, as long as we are below 40% relative humidity, then we shouldn't have a risk for condensation. So how would that look like? What would that look like kind of in a report or an analysis? So in this case, we have a system that has a bunch of different, potential critical locations. So we have a corner, we've got, edge of glass, we've got maybe something in the middle of the stack joint. And so we can identify those different locations and say under the specific model conditions, we get a surface temperature of these, right, under specific conditions. That translates to a temperature index. So in this case, we can kind of see this is about halfway between the exterior and interior temperatures, and so that's at the corner, and that's probably our worst case in this particular assembly. And then we get the maximum allowable RH. So, at that corner, if the interior relative humidity was anything higher than 22%, under these model conditions, and I think this is probably negative 18 and on one side and 21 on the other potentially, then if it's negative 18 out and you have interior humidities that are higher than 22%, then this corner has a risk of condensing or of having condensate appear. Whereas the other areas, you can kind of get a better assessment. Simply like looking at all the surface temperatures. You can look at the interior allowable humidities just to get a sense of how risky that particular location is. You can see here, on the back, this location, kind of on the back of the frame, there's not as much of a risk. You're reaching up to over 40% relative humidity. So that's fairly safe under those specific conditions. Now, one thing to kind of take a look at here, especially when we're looking at complex systems, right, is the idea of how do we get these values? How do we do this analysis? Now, traditionally, for a lot of our buildings, we would just use 2D thermal modeling, right? We've got free programs out there, fairly straightforward systems, very square shapes. We've got NFRC, and it really does it works fairly well for the most part. It allows you to capture those temperatures through a characteristic section, a single cut. We would typically imagine that being in the center of the glazing system. But you still have to do kind of modifications, especially when there's intermittent components like bolts. You have to provide a kind of more of an area weighted conductivity to account for the fact that this is still in 2D. Now, what can you notice about this particular picture when considering, if you were modeling this in 2D? What's the first thing that kind of stands out from this image? Anybody wants to type in? Be so bold. So yeah. So it's not just condensation on the interior, but it's really that corner where what is going on in that corner. It looks like it's got a little bit of frost occurring there. Over here, it's all it's still condensing, a little bit less on this edge. But if we were just to do a 2D analysis through here, we would just get surface temperatures that are above zero. But if we were to look at the corner, why we have temperatures that are below zero, and it's causing this to frost over. So that's something that's missing when we're only looking at it from a 2D perspective. It's not able to capture that. So let's kind of take an example here of a more complex glazing system. So you can see here, it's a curtain wall system, but it's got this kind of spoke here. Now, if you were to do this in 2D, are you able to capture all that well? So here's kind of a look at what we would do as a typical analysis for a glazing system, right? We have our 2D section here with certain temperatures under our climate conditions. Now, what is that temperature at the corner there? It's about roughly 4 degrees or so if we were to kind of pinpoint it off this temperature graph. And really that's because we're these 2D analyses are assuming heat is only being able to flow kind of in one direction through the system. It's not able to go sideways or anything like that laterally. So now, though, if we take that back and actually try to look at that from a 3D perspective, right? Now we're able to account for all of those mullions that essentially butt into each other and or create that larger thermal bridging kind of pinpointed area, right? And what does that do to the temperatures at that location? In a sense, if as we get to farther out from that area, that should probably line up pretty well with our 2D analysis, right? You've got all of these, very consistent temperature gradients. So that should line up fairly well, but you're not really able to capture that intersection of all these different components simply by doing it in 2D. So if we kind of take a look at what those results could end up happening, what you could end up getting, we've got under different exterior temperatures, we've got our T1, so that's at the middle of the spoke. We've got our top edge, so that's probably the most applicable one for comparing to 2D. So if we were to find those same conditions as was modeled in the 2D analysis, yeah, we're not too far off. We're still a little bit lower, but we're not too far off from what that 2D analysis was showing, in the middle of that window system. But when we take a look at that corner, though, we're actually almost at that 0 Celsius, right? Like we're almost to the point where we're dropping below the freezing point. So, can we be missing something, somewhat critical here by only doing these types of complex glazing systems in 2D and doing those estimations based on that? So when looking at this, doing 3D modeling for these types of systems help capture a little bit more of those monthly dimensional features that can have an impact on condensation. And, it's not always going to be a negative either. In many cases, if you have, heated frame, or you have high conductivity frames, that can sometimes bring more heat to those surfaces, laterally during different intersections than what you could potentially capture in 2D alone. And it really just helps to account for more when you're making those assessments of what the first condensing surface and what those temperatures could be, right? About capturing maybe those corner pieces or those intersecting components. And really, do you need to do this on every, marquee project? No, it's really necessitated by the project requirements. Like what level of accuracy do you need to achieve in order to feel confident that you can proceed with a design or that a particular system is suitable for your particular project? So that becomes a bit of a discussion with the design team when that is required. To kind of look at a case study here of putting all of that that assessment methodology together and really making it work on a project. So in this case, we have an event hall that has some skylights. So you can kind of see here that this image is looking up, and you've got this whole row of skylights right along the top of the building. So it's a key architectural feature. It's bringing in natural light into the main foyer. But at the same time, you don't want it to be so cold that if they have a big event going on here that has elevated levels of humidity, that you're going to get water droplets dropping on people below. So it's very critical to make sure that this system performs effectively. So when we kind of take a look at doing some of this modeling and looking at it in a 3D perspective, they've already gone with triple glazing. It's in a particularly cold climate, so they've tried to do their best in terms of best practices for the design to prevent that condensation from happening. So when we've modeled it now, we can actually start to get what those temperatures could potentially be on this project under certain conditions. So when we've gone through our modeling process, we identified, again, it's probably going to be that corner area. Doing our first model, we see that those temperatures are the lowest in the corner area. At the underside, where all those mullions intersect. So looking at it from 3 different temperature scenarios, we have our average low temperature for the winter, at about -25 degrees. We have our design temperature. So the design low temperature is at -40. And then the very extreme low, because remember, they're trying to prevent as much condensation from happening even at these very extreme time periods. So even at an extreme low, we can get a temperature there. And then we can, use the temperature index as an ability to kind of look at what potentially the temperatures could be when we have exterior temperatures in between there. We don't need to, explicitly model it. We can use the temperature index to kind of get an idea of, between these two sets of temperatures, what the surface temperature could be. Right. So we were able to kind of identify not just the surface temperatures, but with the 3D modeling, we can actually use it to identify the extent of where this condensation potential could happen. So in this particular building, they want to control the humidity at about 40% RH. And so that leaves, and leaving it about 22 degrees on the interior. So that's around a dew point of 8 degrees Celsius. So if we use 8 degrees and we, kind of, make everything else that's higher than 8 degrees, because we're not concerned about, temperatures above the dew point, anything that's sitting below that dew point of 8 degrees. And so you can see, the system performs pretty well. There's maybe a little tiny piece of condensation potential here of lower temperatures here, but that will probably be picked up by the condensate track that usually runs along these skylights. So under normal conditions, that may be so small that you're potentially not going to get condensation there anyways. Now, as we get to more of the design temperature, that 99% of the time, now remembering that probably less than 1% of the year is going to be like this, all of a sudden we start to see, along the edge of the glass, still a fairly small amount, less than 10 millimeters off, less than an inch off the glass. But you start to see that starts to have more of a potential to form condensation. Now, what do you notice about this system? When we start hitting some of those extreme temperatures at -53 degrees, which is significant, right? That's factoring in wind chill and night sky radiation and all that. But that's pretty cool. But what's one thing that you can kind of notice here about this system where condensation is starting to form? So the big thing here really is that it's actually starting to form also not only on the glazing systems, but on some of the detailing, the wall sections as well. This may have potentially a steel stud bracket here, and it may be that some of this heat it's not fully insulated enough, especially at this joint, that is causing that these temperatures along the backside of this wall are now also starting to hit below the dew point. So you could have issues not just with condensing on a glazing portion, but maybe even on the backside of whatever this framing system is back here. So this helps identify not just small sections within the window system, but also kind of bigger picture of what's going on around the window system as well. Now, how do we take that information and make it a little bit more applicable for our project? How do we assess the risk now? So let's assume that, say, they didn't control the interior humidity to 40% all the time. We can actually put all of that information together. We can take the surface temperatures that we know that are created by specific exterior temperatures. We know our temperature index, and we can get our maximum relative humidity. And we can essentially create these graphs for the key sections. So in this case, we have the corner of our skylight, and we can highlight, well, under what conditions will interior condensation have the potential to form at that corner, right? So we can identify all of those targets, and essentially anything below this line can potentially be at risk. So if we have 40% relative humidity, then anything between somewhere around negative 24 and lower in temperature has a risk of condensation. At the same time, if we know we're somewhere around negative 20, then we know we can look down here and we know we can't really go too far off 40% RH. So we kind of look, where the conditions are that create that potential risk for condensation over essentially the course of the year. It's not just looking at design situations. You could have this potentially occurring depending on what these conditions are throughout the rest of the year. So where can we take that even further? Well, if you really wanted to get down into the analysis of this, we could actually start utilizing hourly weather data to kind of better understand what the frequency is of when those conditions occur that could lead to condensation. So we could take, historic weather files similar to what they use in energy modeling, right? With the inputs that they use, and that's, essentially a typical year. It's not a particular, it's not a, it wasn't necessarily 2017, but they take, worst case scenario months from different years over the last 15 years and use that information. So we could take that. We have, it contains, your exterior temperatures when you have, bright sunny days, which may, lessen or increase the temperatures on the glass so that you don't have that worries about condensation. It has wind speeds on the outside. It's got, clear night skies if you're worried about night sky radiation cooling down surfaces. It's got exterior humidities. So it's a lot of this information that we can use to then further assess what the risks are. So we can find out, if there is a risk of condensation, how long does it last? If a surface drops below the dew point for an hour, is that really that big of a deal? You're going to have a lot of condensation appearing that's probably just going to be taken away before it gets absorbed into materials within the next hour back into the air once the air heats up or surface temperatures rise up again. So that helps us get a little bit better sense of what the actual risk is for these surface temperatures. So in the case of this event hall, looking at this particular location, we were able to kind of look at how many of these wetting events occur, and if it's over the course of the winter months. So in this first case, we see it happened 4 times over the winter where there's a wetting event that was less than 5 hours. So the likelihood that it's probably going to be taken away before anything really happens to the materials around it. Now, this one, though, is probably the more concerning bit, right? You've got wetting between 5 and 10 hours. So that's has some indication that it's not just a little patch of area that can have potential condensation, but it could be a larger area that sticks around. It stays colder for longer. Then you have a situation where maybe only once you have something that happens for almost half the day, right, where you have condensation appearing. So then it becomes a bit of a back and forth with the design team. It's like, is this acceptable for the project? Do we need to have further mitigation? Do we need to look at mechanical solutions? Do we have to put in baseboard heaters around these locations? Or do we just crank up the temperature when we know that the temperature is going to drop potentially at certain times of the year? So we just anticipate that, crank it up so that we don't have to worry about these events happening. So it's kind of gives an idea of how you can proceed with addressing some of these condensation risks. Now, just understanding, before going into a bunch more of these case studies, is that this is all done through modeling, and it's through tested or simulated results, and really it's whether it's tested or simulated, the results are only as good as what you include, right? So you have to kind of factor in some of the assumptions that go into these analysis, and as you try to reduce some of those assumptions, that probably takes longer. It takes more analysis or more complicated ways to analyze these systems. So typically the first one that we think about is that any of the air inside when we're doing these assessments is well mixed, right? It's the amount of moisture in one part of the room is going to be the same in the other. The temperature in one side of the room is going to be the same in the other. So all the way up to the glass. So helps realize when we set our conditions in there. But that may not always be true, and it doesn't often include the benefits of solar heating. So if you have sun hitting the surface of your window, that's going to up the surface temperatures, right? More than what the exterior air is going to decrease those temperatures. So how do we include those benefits of solar heating in order to reduce those wetting periods or those amount of times that we think that that surface is going to be below the dew point. And it also doesn't necessarily include for obstructions, right? That would prevent air movement from reaching the window. You don't want to create, no building really wants to create dead air zones near places that could have a lot of issues with condensation or a lot of thermal bridging. Because if you don't have that air movement, then you have moisture that can potentially build up there, and then not able to take away any condensation that forms into the air. So it doesn't necessarily account for that. When you start doing a little bit more thorough analysis, like if you start getting into like computational fluid dynamics and really doing airflow analysis, you can go that level, but it really depends on what you need that for, right? Again, how complex you need to make your analysis to meet the requirements of the project. So let's take a look now at a couple of these where we have these kind of complex glazing systems and what the requirements were for these projects. So in this case, this is an arts center that has very large curtain wall spans within the main foyer and event space. And really they want to have that floor to ceiling multi-story glass view out to the exterior. And part of this feature is a timber mullion that has an exterior aluminum attachment, steel carrier to hold the IGU in place. And they also have an exterior fin system, right, that essentially penetrates through the entirety of the mullion. Kind of give you an idea of what that looks like in a 3D rendering. You've got your timber mullion at the back. Here, you've got your attachment system to that timber mullion, but then you've got this aluminum kind of half frame to hold the IGU into place. And then you have these fins that stick through the system and essentially pull back through in past the IGU, which is your thermal layer. So, in this particular analysis, they wanted to look at, well, what are the options? We know that fin is going to be quite the thermal bridge. So what are some of the options and what are the impacts that has on the condensation potential on the interior side? So we go through our thermal modeling and we identify those particular critical points, again, in the system. And in this case, we've identified, again, the corner. We've identified the edge of glass through the field of the wall. And then looking at different, different points of the system of where it's located, whether it's right at this bracket or right in behind where the timber mullion, the timber mullion is hidden in behind here, but an area where interior air is harder to get to take away any kind of moisture buildup that's there. So after we've identified all those particular items, now we can look at those surface temperatures themselves and find out, well, what is the risk here? And we've separated it in by these different situations. So, if we had an aluminum fin that's the basis of design that's much more conductive, or do we go to a stainless steel fin, which is much less thermally conductive? Does that make an impact? Kind of looking at this, does this make an impact for the glazing corner? Does it change much? Maybe a little bit. 21 allowable interior humidity, 22% to 23%. It doesn't really change all that much. But if we change it to obviously aluminum fin to a warm edge spacer, yeah, we're going to get a bump up in those surface temperatures simply because we have a better spacer. Glazing edge, yeah, not much difference between the different systems except for when we go to a warm edge spacer. But if we start looking at the vertical frames, right, we know that fin is penetrating back into the attachments, the metal attachment system. So here we can see, if we started to change around what that frame material is, all of a sudden, yeah, we do start to get a little bit more of a bump up with what those surface temperatures are on the framing. Similarly, for different locations along that vertical frame, yeah, we see an improvement that can help, right? And in a lot of cases for condensation, it's, you may just want to hit certain thresholds, right? In this case, we know maybe they're trying to maintain the spaces at 40% relative humidity. So as long as we can get something up to that level, that may be what they need to hit that threshold and be comfortable with it. You know, it may be not a huge, earth-shattering improvement, but at least it gets them to where they need to be in their design, and that's enough. And again, we can kind of take a look at this under specific conditions. Well, what is the area of risk of condensation? So again, looking at this system, when you take away that timber frame mullion, what are our risks of condensation under those different scenarios? When we're looking at potentially a design situation where we have interior temperatures and our dew point is at around 6 degrees, and you can see as we look at different situations, not a whole lot changes between the aluminum frame and the stainless steel, or the aluminum fin and stainless steel fin on the outside, obviously, as we discussed. But as soon as you hit the warm edge spacer, yeah, you all of a sudden eliminate a lot of that corner condensation and reduces this to potentially less than, maybe only a couple millimeters off the frame. And whether or not that's enough to actually, enough of a surface to have condensation form, that's a good question. But at least now we know that the extent has been reduced. Another situation where we're looking at these anchor penetrations within curtain wall systems, this is always a big question, is like, if you put anchors in through past the thermal break, does that cool down the interior mullion too much, and do you get a risk of condensation? So in this particular case, we have a system that has a couple different penetrations to hold up, again, an exterior fin. So going through, we identify our critical surface temperatures, critical areas, whether it's on the vertical frame, or underneath in the spandrel panel area, or underneath where you have the floor supports. So where are probably the likeliest of the coldest temperatures? In this situation, again, looking at some different scenarios, if you didn't have that bracket there, what the baseline kind of temperature would be. You can see here, at the corner, it's about 7.7. If you have the bracket there, it actually cools down the corner decent amount. But really, it's all occurring in that frame, so that T2 area, that vertical frame area. So if we started with about 13 degrees, that's pretty high, that's pretty warm. All of a sudden, when you put that bracket in there, it drops down to that surface temperature about -5 in this case for this particular building, and that's you essentially create these frost zones, and that's not something anybody wants on the interior of their building. So what can you do? Are any of these solutions, from trying to create a thermally broken strut, a thermally, on different areas where you thermally break it? Yeah, I mean, you improve it by putting that thermally broken system, but again, you still haven't reached popped over that threshold of frost protection, right? So, are your interior conditions going to be over 24% relative humidity? If so, then yeah, you could potentially still have a problem. And this may lead to other solutions, whether you get, you reduce the amount of brackets, or you try to find a different type of thermally broken bracket, or maybe, again, you're looking at those times of the year where you have to increase space heating in that room or in that particular location. Another good one here is looking at a sports stadium, right? And a lot of sports stadiums are now moving towards using these ETFE panels. So instead of using large glazed systems with glass, they're using these polyethylene films, these clear films that still give that visual light through, but still have some sort of environmental separation. Now these can kind of come in a couple different versions, right? You've got these ETFE pillows. They can be a single film, so you can, if it was just that green line that's there, so it would just be a single film that's suspended across the whole thing. Again, not a whole lot of U value out of that, but it provides that environmental separation. You can get a pillow system, so they have two films that are out there, and then on the inside they just kind of fill this with provide some ventilation of the system. They blow in air through these pillows through the whole thing to keep it inflated. Or you can get try to get even better system with better U values out of it, and they would put a 3 film. So you get the film here, so it creates almost like trying to mimic a double glazed unit with 2 air pockets. But really looking at this, where's going to be your critical area of where condensation can occur? Really, it's at each of these frames, right? These pillows need to be pinched in, the films need to be pinched in, and it comes down to a spot where essentially you have almost no thermal insulation at the point where these two films meet. So how much risk is that? And is there enough heating from, say, the framing around it to keep that warm enough? Let's take a look. So let's take one situation here where they have a ETFE wall that's going up. That's a single film. So they have some sort of structural connections along the side, and then little small struts that attach to the framing. And then one of the questions here was, do you include an isolator pad between the window system or the ETFE system and the struts, right? Does that do anything? Does that help us at all to reduce condensation risk? Well, if we kind of take a look at these systems now, with and without the pad for different locations, well, between the two, you're not really doing anything because, frankly, putting an isolator pad inboard of the window, it's not actually doing anything. If anything, you are preventing heat from getting to the window frame to help warm it up, right? So looking at this type of system, where is our critical surface anyway? And that's really wherever we have the lowest surface temperature or the lowest maximum RH. So in this case, it was where these suspension cables meet with an overlay film that goes over the top to keep them in place. And so if any air got inside this little pocket, that would probably be the largest risk of condensation occurring within that cavity. Other than that, it's really at your glazing interfaces, right, where you have the framing material around the film. Similarly, we can take a look at an ETFE roof. So in this case, where is going to be our coldest or critical temperature location? Let's take a look. Kind of looking at one section of this roof area, we can see here that you have these large I-beam structural connections, and then you have these little struts that help stand off the ETFE framing, off the main structural support. So we get these situations where right up against the framing is probably where our coldest temperatures are going to be. Looking at this from when we actually put some numbers to it, it's kind of interesting here is where these surfaces are the coldest are actually in the center. These struts are actually being able to bring heat, like I mentioned before, to the frame and actually keep the temperatures right around that strut warmer than it is in the center of the ETFE frame. And if you look here, under these specific conditions, yeah, we've got pretty high, pretty acceptable RH and surface temperatures. But as we drop down to lower temperatures, all of a sudden we get pretty low allowable RH, right? Like your surface temperatures are pretty cold, and our allowable RH is pretty small at that point. So what can you do in those situations? And I think in this particular case, the decision had to be made whether or not you put some supplemental heating systems, whether it's baseboard heaters or some sort of unit heating system, that when this occurs, they can turn that on and keep this whole area warm, so that you don't risk condensation falling down onto the stands. One of them that I thought was pretty neat is looking at double facades, and I don't know if anybody here has had any experience with these types of buildings. But really, it's essentially creating a second skin on the building. You have your primary, envelope back here, and then this kind of interstitial space that could be, buffering the temperatures here, so you don't see as big of a temperature difference across the system itself. But usually, this space is vented, or it has some air movement in it to take away any moisture buildup, or take away any prolonged dead air spaces that are in there. Now, we had a project that kind of wanted to take a look at this of how they could create this double skin facade, but not necessarily could they avoid the mechanical venting between the spaces. And it's really, the intent here was to use it for a music hall. And, the first intent was, to have large places of glass so that for recitals or different performances, they could see out and get a nice kind of feel for the surrounding area along with the music to kind of, have a nice experience within that space. But at the same time, they wanted to have an acoustic buffer. So having those two large air spaces in there can help reduce some of that noise transfer from the exterior. You can't necessarily guarantee that this system will be perfectly airtight. So, typically they would do mechanical venting, but if you want to avoid that, well, what are our solutions to that? But first and foremost, what is the risk? What would happen if warm, moist air got into that cavity space? So what we did is we took a look at probably the worst case situation, and that's in an isolated corner, right? You're going to have less movement in a corner than you will, especially if you have these columns or whatnot, than in comparison to other areas of the facade. So we're able to kind of take a look at what happens at top, somewhere, some middle space, and at the sill as well, just to get a sense of, well, where are the riskiest points? And if you look here, you can see the blue temperatures being the coldest temperatures really being occurring at that corner space, being the farthest away from that interior heating. So this analysis, we can get all those surface temperatures, and that can be compared with the mechanical design and the occupancy schedule. So we worked with the mechanical designer to really figure out, okay, these are what we're showing as the worst case scenarios for these temperatures. So what are the interior conditions like? Are they going to fluctuate? What do we have to worry about? At what times of the year, what situations are we going to have to worry about that those surface temperatures that we've identified are going to be below the dew point? So they, this being a concert space, they identified, certain levels of when the dew points over the course of particular days, and when they have, the amount of people that increase, maybe for a concert at a certain time of night, all of a sudden that bumps up the amount of people, and the dew point starts to raise because you're increasing the amount of interior humidity because of those people. That can then be correlated back to those hours of wetting or how many annual hours there are that may be below the dew point, and that gives them an assessment of how risky this system would be for reducing mechanical ventilation to take away that moisture. So in the end, I believe this project went and decided that it wasn't feasible, and trying to do some sort of desiccant layer or something like that wouldn't quite meet the requirements, and it'd be a little bit too much on the maintenance side. So they just had to go with that mechanical venting. So really the idea of using thermal modeling, 3D modeling, when we can to assess surface temperatures can be quite useful on a whole slew of applications, right? It's not just for condensation resistance. We could be looking at, exterior temperatures as well, right? If you're looking at certain locations where there's concern for ice buildup on the exterior, we try to make as energy efficient windows as we can now, but is that, decreasing temperatures on the outside so that now nothing is heated up enough to melt ice on the exterior side, and it builds up, and where it can potentially slide off once temperatures become a little bit warmer. So these types of analyses can be used to assess that risk as well. Similarly, if we're starting to get more triple glazed units, especially on higher end homes or higher end projects, where we get kind of worried about what's the risk of fogging on the outside of the glazing units, right? Are we under the right conditions where that can occur quite frequently, and are people going to then blame, the supplier, for the fact that it's like, oh, something's wrong with my windows, I can't see out of them in the mornings. And then we can get even more advanced and kind of looking at even finer tuning, so don't, reducing the conservative estimates of these, where we start, coupling it with, say, more thorough analysis of maybe fluid dynamics modeling or anything like that, to really understand, how is a heating system impacting the temperatures on the glazing system, right? If you put a baseboard heater underneath a window that you're hoping will alleviate all the problems, is that baseboard heater actually getting enough of that warm air to that surface to prevent that condensation from happening? Or is it just, you don't worry about it and just you make a big enough baseboard heater that it just dumps a ton of heat? But of course, that's not necessarily going to meet your energy requirements either. So there's a lot of different ways that we can take these sort of unique glazing system analyses and apply it further on other types of projects. So yeah, that kind of goes over some of these unique systems. Yeah, I just kind of want to open it up now. Does anybody have any questions on some of the material here, or on the modeling procedures or techniques that we use to identify these critical locations?
Thanks, Neil. Thanks very much for that interesting presentation. I do realize for all we are a little bit over time, but we'll still hang around for about 5 minutes for questions. I believe, and may pronounce this incorrectly, but I think Said, you had raised your hand earlier. I'll unmute you, but you may have to unmute you from your end as well. And in the meantime, Said, I've sent you a request to unmute, but in the meantime, if you have any other questions, you can write them up in the query line there. No, not getting Said to unmute. I guess one question maybe while people are hanging around here, Neil, who is responsible for this modeling analysis? Is this something the supplier should be doing, or the design team and the client?
It really depends on the specifications, how the specifications are crafted for this. If these are issues that have been previously anticipated by the design team that ends up in the specifications, that could push this back down to the supplier level or to the trade level. In many cases, it could be that it's something that's identified in the shop drawing phase or something like that, and it becomes maybe a bit of a negotiating piece. But it could be anyone, right? Sometimes this falls back on the consultants on the project. It really depends on how the client wants to proceed.
Okay. And another question is, in terms of, I think you've spoken, there's a lot of inputs and variables that come into this. Can this end up being overly conservative, and especially if we're looking at worst case scenarios? And then, a second part to that as well is, if contractors are receiving specifications with a temperature index, how set in stone is that for them?
Right. So, I mean, temperature indices, again, are intended to apply to any situation. Normally, I would say, I think even with the element standards, if you are getting a temperature index, there's a lot of things that can go in to change that number. It's not specifically constant, because if you think about it, if you have a window air gap, there's a lot of correlations that go in there that could change. Like, you may have a slightly different U value based on the temperature difference across that window, simply because of the amount of convection and different gases and whatever you have in that cavity. So in most of the cases, you will use a large temperature difference to do your analysis, and then that I value becomes fairly, I would say, somewhat conservative. But if you're given that I value, you'd have to be pretty well identified of where that location is for that I value to apply. And then, if that's part of the specifications in terms of that analysis, then what you'd have to do is follow whatever the language is in, and then, prove that I value for that particular location is met by your system under the project conditions. And I would say for specifications, it has to be very, very clear as to what it is that they are requesting from that particular I value. Is it something like from AMA under set conditions, or is it a project specific value? So that's kind of where I see that. At the same time, again, like I said, the more assumptions that are put in, likely the more conservative the analysis is going to be. So again, it really depends on what you're using these values for. If the project has very, very strict requirements, then you probably want to be pretty conservative in your analysis, so that they're really minimized, like completely mitigates the risks of condensation. If it's a system where a residential project where typically you're not really able to control the interior humidity anyways, and that people are just going to complain that their windows are leaky, but despite the fact that they have like 10 showers a day and cook all the time. And so you really can't impact. Maybe you don't need to be conservative in that approach.
Okay.
Just to make things a little bit easier. Yeah.
Okay, thanks. Okay, we'll take. I think Said, you've unmuted yourself. I think you had a question, and then we'll take that as the last question there.
Okay.
Hey, Said. No, we can't hear. Yeah, we can't hear you. Okay, well, yeah. I mean, Said, if you have a question, feel free to follow up with Neil. His email address is there on the screen. So yeah, if you do want to follow up with him, and if anybody else has follow up questions, yeah, don't hesitate to reach out to Neil. And yeah, with that, we'll thank everybody for attending, and I hope that you found it useful. And hopefully, you'll be joining some of the further seminars with NBC. Thank you very much.
Thanks, everyone.